All right, hello. Welcome to Day 8, Lecture 20. Today we're going to be talking about some more examples of hypothesis testing. I'm hoping to clear up some of the confusions because I know this topic is really complicated and difficult to understand. Okay, so first, some announcements. Again, forgot to write my announcements down. Here we go, announcements. So office hours this week are office hours on Thursday are moved to 367 Corey instead of the usual 258 Corey location. Office hours on Friday are canceled. Okay, so if you come to office hours tomorrow, come to 367 Corey, not 258. On the midterm, I just want to remind you that you have access. We're going to give you this sheet. Okay, so this sheet, the midterm study guide, we're going to hand it out to you during the midterm, so you don't have to print it out or bring it yourself. You are also allowed a one-sided sheet of paper, handwritten. Okay, so a one-sided like a cheat sheet that you can do yourself, but it has to be handwritten and only one sheet. The midterm will be held Friday from 10 to 12 p.m. in a normal class time. Check our website for your location. Okay, so we have now your location for the midterm. Based on the first letter of your last name, you're going to go to a different room. Okay, so make sure to check the website, know which room you're going to. You have to bring your student ID to the midterm as well. Okay, so go to your room and bring your student ID. Okay. Lab on Wednesday and Thursday, and lecture on Thursday will be midterm review, as I mentioned before. 4 hours of lecture attendance are required this week as usual, but the midterm will account for 2 of those hours. What else do I got? And tutoring is also midterm review this week, so you haven't signed up for tutoring. Do we have any spots left? Nope, no spots. Okay, no spots. Everyone signed up. And that's all the announcements I got. Any questions? Okay, so as always, you can go to our website, check it out here, in case you forget. All right, close that, close that. So if you will humor me for a moment, okay? Please split into pairs and label like one person, person one, one person, person two. And I would like you to discuss with your partner these 2 questions. Okay, so person one, you're going to answer this question to your partner. You flip a coin 10 times and it lands 8 heads. Is the coin fair? Suppose your p-value is 0.12, but talk about how you would go through the process of like stating your null alternative hypotheses, coming up with a test statistic, doing your simulations, do all that stuff, talk it over with your partner, and then once you're done there, partner 2, talk about this question, which is you roll a 6-sided die 20 times and it lands 10 6s, is my die fair? Again, talk about the process, try to explain it to your partner, and suppose you get a p-value of 0.01, explain what that means as well. Okay, so please talk over with your partner, just humor me, try it out, go. All right, let's see if my computer will come back online. Come on, computer. This is problematic. Okay.
What about writing on the board? Doing that old school.
I could do that.
Do you need the charger?
It looks like my computer just decided to give up on me. Okay, let's take this out. I'm going to put it back in. 1, 2, 3. Come on. Come on. Come on. Oh, there we go. All right, we're back. All right. So Sorry for that long break. But so why did I say you have to explain it? Why did I say you have to like talk it over? It's because what you have trouble explaining is what you need to review, right? So I kind of like looked out into the crowd. I looked at your faces. I heard what you guys were saying. And like some of you guys are like, oh, the null is this. Oh, the null alternative is this. Oh, I don't really know what a test statistic is. The things that you have trouble like articulating or explaining in detail, like when you feel like, oh, I don't really know how to explain to someone else, to review, okay? Because when you don't know how to explain something, it shows that you don't quite understand it, okay? So I'm glad you find it funny. So again, I asked you to hear me by talking it out aloud. It's one thing to kind of look at me doing stuff on the board or like on my screen, and you look at that and you're like, okay, I can do that too. It's another thing entirely to try to do it yourself, to explain it yourself, or to actually run through the code and try to come up with it yourself, okay? And that is a level we need to be at in order for us to continue going on with this class, okay? So please, like, remember what you had trouble with and try to focus on those as you review for the midterm, as you listen to today's lecture, as you go on with this class, okay? So let me review really quickly what we talked about, what we ended with yesterday on p-values, okay? So in hypothesis testing, we define two mutually descriptive one of them we require to be evaluated using probability. So we require that the null hypothesis define the world in terms of some probability. So it says this thing has some probability of occurring. My coin is fair, so heads and tails should occur about half the time. My die is fair, so each face should occur 1/6 of the time. Those are examples of valid null hypotheses because they specify a complete probability distribution. Okay. If we decide to reject the null, we accept the alternative. Otherwise, we fail to reject the null. The null still looks reasonable. There might be some other reason. There might be some other stuff going on there, but in that case, the null looks pretty reasonable to us. And the reason why we say this is because basically the guy who came up with all this, one of the people who came up with all this stuff, named Fisher, he said no isolated experiment can suffice for the experimental demonstration of any natural phenomenon. Basically, in stats, we're dealing with uncertainty, right? So anytime we take a sample, it's a random process. We could get really unlucky. We could just roll a die 20 times, and all 20 times it'll land 6. It's possible, right? So we can never really make a hard and fast conclusion when we're doing a hypothesis test. But a hypothesis test can give us kind of a direction to look in, right? It can say, ah, this looks suspicious. You should investigate it further. Okay. So in terms of actually conducting a hypothesis test, step 0 is to go find some data. These are what we call the observations. Most of the time in this class, we'll be doing that for you. But in the real world, you actually have to go out and get some data yourself. Then you come up with 2 descriptions of the world. Okay? So the null, the data come from some well-defined process, and the alternative is something else. Finally, we want to figure out, OK, I went out into the world, grabbed my data. Do my data support my alternative hypothesis, or is there something else going on? Okay, so what we do is we say, OK, assume the null is true. Look at how the world would have behaved by drawing simulations, and then see how likely my result was to occur. Okay, so we choose a measurement of weirdness, essentially. We choose a measurement of distance to say, the higher or lower this number is, the more strange my result is. That's our test statistic. And then we draw simulations and compute a p-value. Okay, so the p-value is, again, by definition, the probability that the test statistic will be equal to or more extreme than the observed test statistic on the null hypothesis. This is a really long definition here, but you really want to just remember, like, OK, draw simulations, assuming that the null is true, see how likely my result is to occur, make a conclusion from there. Any questions about this? OK, so when we were actually computing p-values, as we did yesterday, we took this definition and said, OK, here is my null distribution. So if you remember from yesterday, our discussion about p-plants, we did some simulations. We plotted a histogram of our test statistic, assuming that the ratio of p-plants was actually 3:1 purple to white. We actually plotted those, and we saw this distribution. Our blue line here, which we drew yesterday, was what Mendel observed. Okay, so he observed, I got a value of 0.008, which is right here. It looks like the area in the tail of this distribution is right here. Okay, so here is the area. Okay. Our blue line is our observed test statistic, which is just from our sample, from our data about the world, what did we observe? Then we say, OK, under the null hypothesis, which is this histogram, how likely is it to get my result or something more strange, something more in the direction of my tail? So we looked at calculating this area here. This area here is our p-value, because it's an approximation of the probability of getting our result. Okay. So we talked about some conventions when it came to using our p-value, right? So we say that our data is inconsistent with a null hypothesis when our test statistic is in the tail of our null distribution. By convention, we usually say it's less than 5%, and we call that result statistically significant. Sometimes we say we want something more precise, so we say less than 1%, and that result is highly statistically significant. But these are just conventions. You can draw them arbitrarily. It's just whatever is more convincing to you. All right? So that's a recap of what we did yesterday. Were there any questions about what we did? Yes, Chase.
How exactly do you draw the blue line? You say it's an observed thing. Is it just like an average?
Yeah, so Chase is asking, where does blue line come from? Okay, so what we did was Mendel actually grew some plants. He grew a bunch of plants. He found that maybe like 76% of them were purple. We define our test statistic as how far away you are from 75%, which we think is a real proportion, the real ratio. So we said, OK, if the world was actually 3-to-1 purple to white flowers, how far away will we get from 75%? So it looks like most of the time we're pretty close to 75% purple. Sometimes we're 76% purple. Sometimes we're 77% or 73%. And what Mendel said was, or what we did here is we said, OK, here's what we think the world would look like if we actually do, if the actual ratio is 3-to-1. Here is Mendel's data. Don't know why that's bouncing. OK, go away. Come on. Oh my God. Oh my goodness. Oh gosh. Go back. OK. So here, right here, is our null distribution. We say, OK, if the world was actually 3-to-1, here's what we expect our test statistic to be. The blue line here is what Mendel observed. So given our data, is our data actually likely to occur if we assume the null is true? Does that answer your question?
Yeah.
OK. We're going to do some more examples here today. If you still have questions about it, come talk to me after class. I'll try to explain it in more detail. OK, so some conventions. And now I have one more activity. So if you would please pick a number between 1 and 100. OK, so come up with a number in your head. Think about it. Pick wisely. I look into your eyes and I see a number chosen. All right, let's move on. So let me make a brief stop there. So remember that number. Let me make a brief stop here and talk about test statistics, because I noticed that this is a question that a lot of people have during class or during office hours. Okay, so when we choose a test statistic, we have a bunch of options, right? So for example, yesterday when we talked about p-plants, we did like some absolute value minus 0.75 thing. And then I asked you a question of what happens if I remove the absolute value? What happens then? And in homework 5, we ask you a question, which is like, which test statistics will actually get you like some actual good hypothesis test, right? And basically, the criteria for choosing a test statistic is we just want to be able to say, OK, if my null is false, then measuring my test statistic should help me reject the null. And what that means is, OK, the farther away I am from what I expect, the more different my test statistic should be. And let me give you some examples of that. So take the numbers you got in your head, and that is your coolness level. OK, so it's not the weirdness anymore. It's coolness. OK, so I can ask the question, is Sam cooler than the class? All right. So let's say I chose a coolness level of 85 because I'm pretty cool, right? How many guys? Let me do this again. So how many guys got a coolness level of at least 20? At least 20. Okay, at least 30. At least 50, at least 80, at least 85. We got a couple less people than last time, I guess, because people didn't want to be weird. But it looks like we have about, what is that, like two people that got 85 at least. Okay, so what I'm doing there is my test statistic is just my coolness level, right? Because what I'm doing there is I'm saying, OK, everyone who got 85 or above, that is what I would consider that is actually my p-value in this case. Okay. So again, I'm trying to figure out the probability of me getting my coolness based on you, the population. The way I calculate that probability is by looking at how many of you guys have at least 85 coolness. And I say, OK, if I came from this classroom, there is about, let's say again, there are about 50 students here. There are 2 students that got a coolness level of 85 or above. So I say, if I picked one of you guys at random, there's about a 4% chance that I'll get a coolness level of at least 85. So for me, the chance that I have a coolness level of 85 is about 4%. So my p-value is 4%, or 0.04. I would say, yeah, it looks like I am cooler than the class. On the other hand, I can ask the question, am I less cool than the class? Okay, so then I can say, oh, I got a coolness of, let's say, only 5. I'm only 5 cool. I can ask the question, how likely is it to get a 5 cool, to choose a 5 coolness or anything below, right? So let's try that. How many of you guys got 5 or below? Picked 5. OK, like 4, right? So that means that if I picked at random from you guys, there are 4 out of 50, that's an 8% chance. There's about an 8% chance that if I picked one of you guys at random and set my coolness to your coolness, I would get a coolness level of 5 or below, right? So there's about an 8% chance of that. And so I can answer that question with that test statistic. So the test statistic in this case is the same, because it's the coolness level. I didn't do anything to that number. I just said take that number and compare it to the rest of you guys. On the other hand, I can ask the question, am I just different? Am I just weird, right? So if I'm just weird, then what I want to ask is, OK, how far away am I from the average coolness, right? So let's suppose that you guys picked randomly 1 to 100, and the average should probably be around like 50, right? So let's say the average is like 50 coolness for everyone. I can ask the question, OK, I got 85 coolness. I want to ask, how different am I from the average class? So if I take 50 and look at what I chose as my coolness, 85, right? I'm about 35 away from the average. On the other hand, I could ask, OK, if I chose a coolness of 5, I am now like 45, a distance of 45 away from the class average of 50. Okay? So in that case, what I want to do is measure how far away I am from the middle, not how far away I am in the positive or the negative direction. That's the case where I want to use the absolute value. Okay? So what I would do there is I would take my coolness, subtract it from the average of 50, take the absolute value. That gives me the distance I am away from 50. Okay, Kevin?
For the last question, is Sam just different? I know you said absolute value, but on a bell curve, would that be like a two-tailed test?
So Kevin's saying on the bell curve, would that be a two-tailed test? Yeah, so if you would imagine for a second, let's say I take all the coolness values that you guys chose right now and plotted them on a distribution. And it just so happened the distribution, most of you guys chose around 50 and went kind of up and then down like this. When I'm asking the question, am I just different? What I'm trying to do is find the area on both sides. Okay. The first question, am I cooler than the rest of the class? I'm trying to find the area of my coolness and everything above. So 85 and up, find the area, find the probability of getting that. If I ask this question, am I less cool than the class? I take my coolness, which was 5, go down, right? I'm going downwards in a negative direction towards 0. If I'm asking a question, am I just different? Am I just far away from the middle? I need to go both up and down. The way we do that in this class is we subtract out the middle value and we take the absolute value. Okay? So instead of looking both up and down, I absolute value everything, and then I can just look in one direction. So for this question, I want to ask how many people got my coolness or above. In this question, I want to ask how many people got my coolness or below. In this question, I want to ask how many people were further from the average than me. Okay. So the first 2 questions here, my test statistic is just my coolness level. I didn't do anything. I didn't change my coolness level. I didn't subtract anything from it. I just left it as it was. In this case, I'm asking this question. I got 85. In this question, I got 5. I didn't do anything to my coolness level. In the third case, now I'm changing my test statistic. Right? I'm saying, OK, if I want to measure how far away my coolness is from the average, I have to subtract out the average and then take the absolute value. That gives me a measure of how far away I am from the middle. So do you have any questions about that? OK. So what about the p-plants? So think about that, and let me show you what we did yesterday. So now that you kind of had that in your mind, let's see if you can again take a look at this question that I asked yesterday about the p-plants. All right. So here's the same stuff I did yesterday. Okay. So here's my null distribution. There are 929 total plants. Let's say 705 of them were purple. And what I did yesterday, if you recall, is take the absolute value of the proportion of purple flowers. So I take my purple, divide it by the total plants, and I subtract 0.75, and I take the absolute value of that. That gives me an observed statistic of 0.008, as we did yesterday. Again, I'm going to run simulation, run this. So this is the same thing as we did yesterday. Here's a familiar looking histogram plus the line. This is Mendel. We said yesterday that the p-value was 0.55. Okay, so the p-value is 0.55. His result seems to be pretty likely to occur by chance. That's what we concluded yesterday. So then I asked you, what happens if I remove the absolute value? So here's the same test statistic. I just removed this absolute value. So before this was here, now it is not here. I run it. I run that. And I notice that my p-value also changes. Talk over with your neighbor what happened. Now we've gone over this stuff about test statistics. Okay, so go.
How many times is the statistic greater than the observed sample greater than this? It's slightly different because now we're looking at it on a belt.
Okay, so what happens if I remove the absolute value? My distribution changes, and my p-value changes too. Why did that happen? Any opinions? Let's try to get one more person. Anyone have any guesses? Take a guess. It's okay to guess. Being wrong is how you learn. So in my coolness example, I had these two were not absolute valued, right? If you recall. This third question here, I said I needed to take the absolute value, right? When I take the absolute value, I'm measuring the distance away from the average. In these two cases, I did not take the absolute value. So in this case, what I'm doing is I'm taking away the absolute value from my test statistic. How does that change my analysis? Sure, in the back. Yeah, so your name is Elias. So Elias says it's taking into account the negative distance from the mean. Yeah, so we look here and we have negative values, right? What happened to these negative values before? Before we were doing the absolute value, so these negative values here, they'd all become positive, right? So they all like flip over and jump over to this side of the 0. And in the case before, So right here, what does this represent? This represents like 70, this is a negative 0.04. This represents a case where we got 71% purple flowers, right? Here, 0.02, 73% purple flowers, right? At 0, we have 75% purple flowers. At 0.02, 77% purple flowers, right? So here I'm measuring. So I say, okay, 0 is if I got an exact 3:1 purple to white pea flower ratio. If I go below that, I'm going to put those here. If I go above that, I'm going to put those here. Okay, so that's a good start. What else does that mean? So what changes? What am I measuring differently? So I changed my test statistic. That means that I'm making a different measurement. What am I measuring with this test statistic? Kevin?
Use the absolute value. I think you're measuring just the distance away, right? You said that here, you take that away. Directional.
Yeah, that's a good point. So Kevin says, when I was taking the absolute value, I'm looking at the distance away from what I think is my average, which was 0.75, right? So when I was looking at the absolute value, I said, okay, 73%, 77%, those are all different. Those are some distance away from my average 75. When I'm doing the absolute value, I'm just looking at how far away I am from 75, just like how in the coolness case, when I took the absolute value, I'm asking the question, how far away is my coolness from the class average coolness, right? When I'm taking the absolute value, I'm just looking at how far away I am. When I remove the absolute value and then look at this distribution, what I'm asking is a different question. I'm asking how likely am I to get 70, let's say what this was, 71%, 76% purple or more than 76%. I'm no longer asking the question anything like, I'm no longer asking the question this or farther away from 75%. So when in absolute value, I'm asking, I can be far away in both the positive and a negative direction. If I don't use the absolute value, I'm now asking the question only in the positive direction, how far away is my result, right? Which means that because I'm only asking the question, look at 76% or higher, I get less area right here. Because before, I took the absolute value, which means that this histogram here is like mostly symmetrical. So I cut it in half, flip one side over to the other side, and that essentially doubles the amount of area in my curve, right? When I don't take the absolute value, now I have less area, which means I get a lower p-value. And in fact, the p-value is about half the previous p-value. Because I'm only looking at one side. I'm only looking at one side instead of flipping the other side over. Okay? So when I change my test statistic, my alternative hypothesis changes, right? Before I was asking the question, okay, Mendel thought that the proportion of purple to white was 0.75, so 3:1 purple to white flowers. My alternative hypothesis, when I originally did my analysis, was he wrong? Is it different than 0.75? Is it different below or is it different above? I'm just asking, is it different? Okay, so it could be different both below and above. My alternative hypothesis is it not 75%? When I change my test statistic, I'm changing my alternative hypothesis to say, okay, he thought it was 75% purple, but I think it's above 75%. So my null is it is 75%. The alternative is it's above 75%. Okay, so I'm changing my alternative by changing my test statistic. So when you're choosing a test statistic to use an hypothesis test, generally speaking, you have to craft your alternative hypothesis first. Okay, so choose your alternative first, and then figure out, okay, does my test statistic measure my alternative hypothesis? Typically speaking, that means that if I'm measuring just, is it different? So if I think my coin is fair, and I'm asking the question, is my coin unfair? Then I want my test statistic to have an absolute value in there, so I can account for both lower than average and higher than average. If, on the other hand, my alternative is my coin is biased towards heads, then I usually don't want to take the absolute value and just take the value as it is. Any questions about that, Kevin?
Would it be wrong if if I just use the absolute value and then got my p-value and then just cut it in half?
Yeah, so Kevin asked, so you're saying I can just, so I ran the same hypothesis or different hypothesis test on the same data. Why can't I just say, oh, OK, the first time I did it, I got a p-value of like, let's say 0.7. And that wasn't good enough for statistically significant. So why can't I just remove the absolute value and say, now my p-value is 0.35 or 0.035? I'm going to get to that in just a second. But it's a good question. So you actually should not run the same hypothesis test on the same data set. That changes the meaning of the hypothesis test. I'm going to talk about that in just a minute. But it's a good question. Yeah. Any other questions? Now is a great time to ask a question. Alan?
Yeah, I have a question about the homework. So, well, when we are determining whether a coin is fair or not in casino, do we need to consider the situation in the left-hand side tab?
Yeah, so Alan's asking if I want to figure out whether the coin is fair or not in the casino, do I have to consider both sides of the distribution? The question is, it depends on your alternative hypothesis. Okay, so if your alternative hypothesis is just the coin is not fair, then it could be more likely, it could be biased in either direction. It could be like, oh, I get more heads or I get more tails than usual. On the other hand, I could ask the question, is my coin biased towards tails? And just ask that question. In the case where I just want to figure out whether the coin is unfair, I would want to take an absolute value somewhere in there, probably, because I want to figure out, is it far away from half and half? Otherwise, I want to take the value by itself. I believe that's what we're looking for.
If my coin is unfair, then it makes the customers lose more money. Do I really need to care?
So you're saying if the coin is unfair and it makes the customers lose more money than usual, do I as a casino owner care? Probably not. So it depends on, and again, it depends on the context in which you're asking a question. But you have to ask the question first, and then you can figure out which test statistic to use. Kevin?
So on the homework, because alternative hypothesis is like the person cheated by trying to get more heads, then would it be a right tail test?
Yeah, so if the question is the person cheated by trying to get more heads, then you're asking the question, I want to know whether the coin is biased towards heads, right? So if you're asking the question, is the coin biased towards heads, then and your test statistic needs to match that question. Okay. All right, so let me take a moment now to take attendance. Okay, so bit.ly/data8 at d8, sorry. All right, go for it. Okay, so to kind of recap, I want you to note one more thing, which is my alternative can have a direction, right? So we talked before, just now, about coins. We said, the coin can be biased towards heads, or it could be biased towards less heads, right? And in that case, my direction of association differs. I could be different in the positive direction, or a negative direction, or both, right? And so, for example, I can say, smoking has some relation to health, which means that smoking has some effect on health. I want to have an absolute value in my test statistics somewhere to say, it could make my health better or it could make my health worse, right? Or I can ask the question, smoking, does it make my health worse? Then I just want to say, OK, look in a negative direction of some measurement of health. So in my coolness example, I tried to illustrate both of these cases, right? I said, am I cooler than the rest of the class? Look in a positive coolness direction. I said again, am I less cool than the rest of the class? Look in the negative coolness direction. Okay. And if I want to ask the question, am I just different? Is my coolness just really far away from the average? Then I want to take the absolute value and look in the positive direction. Because once I take the absolute value, I get no more negative values. I just want to look in the positive direction. Okay. So this is my coolness. I want to ask, am I less cool than the rest of the class? Instead of taking, so in the p-plan example, we took the slice and we looked in the positive direction. If I'm saying like, oh, is this coin biased towards less heads than before? I would take my observed and look in a negative direction. Okay, so again, it all depends on your alternative hypothesis. Okay, so depending on the question you want to ask, you choose your test statistic, and then you choose the direction in which you look when you actually like draw your null distribution. Okay. This brings me to some clarification points I wanted to make. So Luke asked me yesterday, do the null and alternative hypotheses need to be complements of each other? So do I need to say, my coin is unfair? If I say my coin is unfair, if my coin is fair, then my alternative does it have to be my coin is unfair? It turns out that that's not the case. So I went back, asked some people, and they're like, no, it doesn't have to be the case. So I was wrong. It does not have to be the case that the null and alternative are complete opposites of each other. Because I can ask the question, the null is my coin is fair, the alternative is that my coin is biased towards heads. That leaves me with a third alternative, which is that the coin is biased towards tails. So it does not have to be exact, like split the world into two pieces, like I mentioned yesterday. It just has to be the case that if one is true, the other one is not true. Okay. Yeah, Kevin? Yeah, so if it doesn't have to be complements. For example, I can ask the question, the null is my coin is fair, so half chance to get heads. My alternative could be the chance of me getting heads is 0.7 instead of 0.5. So that means that my null hypothesis is my coin is fair. My alternative is my coin has a 0.7 chance of getting heads instead of 0.5. I can test that using a hypothesis test. Okay. But it turns out that in that case, you can actually flip the null. Like in that case, the probability of getting heads could be 0.3, it could be 0.6, 0.9. So there are more possibilities there that I'm not considering in my hypothesis test. But the point of a hypothesis test is just to decide between two scenarios. It's not really meant to say, oh, the world is split into like two ways of thinking. Yeah.
That means like if I reject the null hypothesis, I cannot accept the alternative, right?
Yeah. So it's Abdul Rahman. Abdul Rahman says that means that if I reject null, I can't necessarily accept the alternative, and that's actually pretty true. Okay, so you actually, if I'm testing between the two hypotheses, that the chance of getting heads is 0.5 and the chance of getting heads is 0.7, if I reject the null, which is 0.5, and choose 0.7, I don't know really for certain whether it's 0.7 or not. I'm just saying, based on my two hypotheses, this one seems more likely. Okay, so I don't know for certain whether either one is actually true. All I have is data to support one hypothesis over the other. Again, you can never make that straight up conclusion that it's my alternative for sure, because the p-value represents the type 2 error, or the probability that I reject a null when a null was true. So there's always some uncertainty when I'm doing a hypothesis test. I'm trying to reduce the uncertainty through various means, but there's always some uncertainty there. All I'm trying to say is my data support one over the other. Kevin?
Wait, isn't the p-value supposed to be the type 1 error? Because isn't the type 2 error like an incorrect acceptance of the null hypothesis, like a false positive, if you will?
You might be right. Let's ask Google. What is type 2 error? Type 2 error accepts a null that's actually false. You're right. So it is type 1. Type 1 and type 2 are just in between the two. It doesn't really matter what you call it, as long as you're clear about, oh, okay, the null was true, but I reject it anyway. Okay, so that's the probability that the p-value gives you. It's an error probability. Okay, so all right, let's keep going. So I have a couple more points. Okay, so one, they don't have to be complements of each other. Two, you should not run multiple hypothesis tests on the same data. Okay, so as Kevin asked, can I just take the absolute value one and change my test statistic to get something that's statistically significant? It turns out that you should not do that, because it changes the definition of a p-value. Okay, so the first time I run a hypothesis test on a data set, I'm saying the p-value is a chance that I get my results under the null distribution. If I were to take that conclusion and then run another hypothesis test, what I'm actually asking in that case is, was a chance under null given that my first result occurred? So there's some conditioning that kind of happens based on what you know beforehand. For example, in the Monty Hall problem, right? Because so let's say there are 3 doors, you pick door 1. Monty opens door 3, and so you're choosing between door 1 and door 2. You have extra information because you chose door 1 first, right? So you know, okay, choosing door 2 is better for me. But if someone were to come along and say, oh, I didn't see which door you picked in the first place, that person would have an equal chance of picking door 1 and door 2. In that case, because that person who came along after I chose a door has less information than me, his probability scheme changes based on mine, as opposed to mine. In this case, it's kind of a similar effect is happening, where if you run multiple hypothesis tests on the same data, you're changing the meaning of your p-value. So your p-value, the number that you get, is actually representing a different thing than you were getting before. Okay, so takeaway from that is, if you want to actually run multiple hypothesis tests on the same data, you have to take out some subset of your data, run it there, then take out a different subset and run a different hypothesis there. So you can't run multiple hypothesis tests on the same data set. That's what's known as data snooping, which is generally a bad idea. It'll lead you to some bad conclusions, because you can imagine a case where I run a hypothesis test, get some p-value of 0.06, and then say, oh, my cutoff is now 0.10. My results are valid, or my results are significant. So you can't really do that. It's just a bad time. You have a bad time. Okay. As I had mentioned briefly before, rejecting the null does not always mean the alternative is true, because the p-value is a probability of making a bad rejection. So to get that in kind of an intuitive sense, let's say that I'm evaluating whether I'm cooler than the rest of the class. We raised our hands, and I saw that there were 2 people out of 50 that had a coolness level of 85 or higher, right? That means that if I had not come from the class, or sorry, that means that if I actually come from the class, there's a 4% chance of picking my weirdness, right? So even though in that case I would reject the null and say, it looks like I did not come from the class, there is still a 4% chance that I came from the class, because there are some people here that raise their hand that got 85 coolness or higher. Okay, so the p-value is a probability of making a bad rejection, which means that there is always some uncertainty when you're making a hypothesis test. Alan?
Right. The p-value you talked about here is the p-value we calculated, or the p-value cutoff?
The p-value we calculate, sorry. So the p-value cutoff will always be defined beforehand. So we'll say, OK, if we get a p-value below 5%, we're going to say significant, or below 1%, significant. The p-value I'm talking about here is the actual computed p-value, right? So in the case of the classroom, there's a 4% chance that if you picked a person at random, you get someone with at least my coolness level. Yeah.
So if essentially your coolness level, like you were mentioning, was significantly outside the bounds of the class, it's either smaller than the minimum or larger than the maximum, would you essentially be not considered part of the sample, because your p-value would be really high?
So Alex, right? So Alex is asking, what happens if I got a coolness level of 110? I'm super cool. What that means is, if I look into the classroom and ask the question, did anyone get a coolness level of 110 or higher? No one would raise their hand, right? Because everyone chose a coolness level between 1 and 100. That means that if I had picked someone at random from this class, there is no chance that that person would get a coolness level of at least 110 or higher. That means that my p-value is 0. There's 0 probability of getting my coolness from the class, which in this case means that I will have no chance of making a bad rejection of my null hypothesis, because in that case, I know for certain that I did not come from the class. Yeah, I'll do it on then.
Can you just apply the definition of the p-value on the P's experiment?
Can I just apply a definition of the p-value? So you're saying repeat that, but in the context of the p experiment? Yeah. So in this case, let's go back to my original example. My p-value is the probability of getting at least this far away from 75%. Okay, so if I choose my test statistic and formulate my hypotheses in this way, this p-value right here, the area here, is the chance that I get at least this far away from 75%. In the case of the coolness, it's the chance that I get at least my coolness by drawing from the class. In this case, it's just saying I get at least this far away from 75% if I grew more p plants.
I mean, the p-value here was 0.5, I guess.
That's right.
Yeah, so it's the probability I would do about rejection.
Yeah, so two interpretations. One is there is a 55% chance that if I grew more pea plants and counted the number of purple and white, that I would get at least as far away from 75% as Mendel did. The other interpretation is if I took that p-value and still insisted on rejecting the null hypothesis and said it's not 75%, it's something different, I would have a 55% chance of making a mistake. Because it's actually pretty likely to get something at least this far away from 75%. Yeah, Kevin?
Wait, I thought the chances for making a bad rejection was the cutoff itself and not the value calculated, because for the cutoff value, anything beyond that, that's when we actually reject. So isn't that our chance of rejecting? And I guess what you're talking about is
yeah, so Kevin's asking, OK, what about the cutoff and the actual p-value? You can think about it this way. So in the classroom example, right? Let's say that let's say I go back to an example where I have a coolness level of 110. So no one in the classroom has a coolness level at least as big as mine. The chance that I make a mistake and say, I actually came from the chance that I actually made a mistake, meaning that I say, I did not come from the class when I actually did, the chance of that happening is 0. Because if my coolness level is 110, there is no way that I came from the class that only got values between 1 and 100. Right? So in that case, even though my p-value cutoff could be 5%, there's a 0% chance of me making that mistake, which is to say, I definitely came from some alien land where the coolness level is like through the roof, right? So the classroom is between 1 and 100. If there is no one in the classroom that has my coolness level or above, the chance of me making a mistake and saying, like I say that I did not come from the class, but I actually came from the class, the chance of that happening is 0. It's not the cutoff, it's the actual p-value.
And what is the actual cutoff then? Like, what is the significance of that?
The cutoff is just some arbitrary value. So we say, it seems like 5% is good enough. We'll just say if it goes below 5%, we'll say it was significant. The cutoff is just some value that people made up a long time ago and people decide to go with. So the cutoff is just kind of made up, and we just use it as a convention, like I make tea every morning. I choose 5% of my cutoff every morning, right? But the actual like mathematical underpinnings of that they're actually not very much mathematical underpinnings. Alex?
The 5%. When you say the 5%, you mean like 5% between the minimum and max, right? So in our case, right? It would be just like the 5% of the 100, right?
I believe so. So let me wrap up really quick because we're out of time. Okay, so I can see your question. I can see the question on your faces. Why is a coolness example easy to get, but other examples are so hard, right? You listen to a coolness example or weirdness example, and you're like, oh, that seems pretty easy. But why is it that when I actually try to do like the jury panels, I don't really understand what's going on? And that's because, well, when we're doing a hypothesis test, the overall steps are all the same, right? Choose a hypothesis, choose a test statistic, do a simulation. But those steps themselves can get a little bit more complicated, right? So in some cases, we saw that the test statistic needs to be more complicated in order to answer a different alternative hypothesis. That's one additional piece of complexity. Another piece of complexity is the sampling procedure needs to be more complicated. For example, in the jury panels, we have to do something pretty sophisticated in order to actually pull out example juries, right? So those are two areas in which your process becomes more difficult to understand, but the overall steps are all the same. And I really want to emphasize that to you because I would like you to go back and take an example that you understand. If you understood the coolness example, take that one. If you understand a coin flipping example, take that one. Take one you understand, compare and contrast it with one you don't quite get, okay? And just look at the differences between the two. You'll notice that the differences are almost always here and here. Okay, so try it out. I'll see you tomorrow.